In this video, we're going to lead into what's going to happen in the next two sections for our surface area and volume chapter. In this case, we want to examine how you find the area of a regular polygon when it doesn't make a special shape. For example, with an equilateral triangle, we can find the area by simply drawing in the height and then using the 30, 60, 90 relationships. For the area of a square, we can simply multiply the length of the side by itself. Hexagons, regular hexagons, when we draw in the diagonals, they form equilateral triangles. But what about the other regular polygons? What about regular pentagons, or regular heptagons, or octagons, or decagons? What process do we use for those shapes? That's what we're examining here. A regular polygon is equilateral and equiangular. The distance from the center of a regular polygon to a vertex is called the radius. We've used that already in this chapter. The distance from the center of a polygon to the midpoint of one of its sides is called the apothem, which we've also used this chapter already. So in general, the area of a regular polygon is equal to 1/2 times A times capital P, where A is the length of the apothem and P is the perimeter of the base. Now, we've already had some experience with A and P throughout this chapter, so here we're just applying those values in another form to find the area of a regular polygon. Now, for the process, you start by finding the measure of a central angle. We'll talk what that central angle is in just a moment. Then we use the trigonometric ratios of sine, cosine, and tangent to find the area of the regular polygon. So here's our general definition. A central angle of a polygon is formed by drawing the radii, plural of radius, from the center of the polygon to two consecutive vertices. The measure of the central angle is equal to 360 degrees divided by the number of sides. So in this case, we are going to, let's approximate where our center is here. We want to draw in two radii, and remember, a radius connects the center of the polygon to a vertex. Now, when you draw in two consecutive radii, what it's going to do is create a triangle where one side of the triangle is the side of the polygon, and the other two sides are radii. Now, because they are radii, they are congruent to one another, which means this triangle is isosceles. The side of the triangle is only equal to, or the side of the polygon rather, is only congruent to these other two sides if it is a regular hexagon. So we have to be cautious of not making that assumption when we shouldn't. Now, in terms of how we can go about finding this particular area, it really largely depends on what you're given. If you're given the length of the side, then we're going to be using maybe sine, cosine, or tangent. If we're given the length of the radius, that's going to maybe affect a different cosine, sine, or tangent value. In other cases, we might be given the length of the apothem. So in some form, what we want to start by doing is finding the measure of the central angle. In this case, the measure of the central angle, as it says, is 360 divided by the number of sides. So here, that central angle measure, which is the measure of this angle in this case, is 360 divided by 5, or 72 degrees. So that angle measures 72 degrees. Now, how is that helpful? Well, when we start to draw in the height of this triangle, it's going to divide that 72 degree angle into two congruent parts. In case of 72, two congruent parts would make each portion 36 degrees. So in terms of how that's going to help us, that's where we're going to set up our sine, cosine, or tangent values for that particular angle. It depends on which side you're given, the radius, the apothem, or maybe even the side of the polygon, as to which of those sine, cosine, or tangent values you'd want to use. All right, so let's examine our hexagon. For some reason, my regular hexagon got a little stretched when I pasted it into my document, but we're going to pretend that it's a regular hexagon. So we start by drawing two radii. As we said, with a regular hexagon, these triangles end up becoming equilateral. Now, as to why they become equilateral, here's where we can start to understand why. Because these are radii, I know they're congruent, which means these two base angles must be congruent to one another. Triangle has two congruent sides, must have two congruent angles. Well, when I take 360 degrees and divide it by 6, you get 60 degrees, which means the measure of this angle is 60 degrees. Now, in terms of the central angles, or the interior angles rather, of a triangle, we know that their measures have to total 180 degrees. So if this one's 60 degrees, then of that 180, there are 120 degrees left, which must be evenly split between these two, which is why these end up becoming 60 degrees each. Well, now we see that the triangle is equiangular. If a triangle is equiangular, then it must also be equilateral. So the relationship between the radii and that central angle being 60 degrees is what's forcing this to be an equilateral triangle. Whereas in this case, where the angle for the central angle was 72 degrees, these two base angles would still be congruent, but they will not be 72. Wouldn't work in the triangle sum theorem to make them all 72 degrees. So it will only work in the case of a regular hexagon that triangle becomes equilateral. Now let's do one more with the octagon over here. We take our central point, draw in the two radii, kind of pretend that they're straight there. There again, radii are congruent, so that's still an isosceles triangle. Take 360 and divide it by 8, and we get 45 degrees in this case. When we draw in the altitude of that triangle, it's going to divide that 45 in half, making each half 22.5 degrees. So keep in mind that as we work through this process, some of these angles might get to look a little more unlike what we'd expect. We're going to see more decimals than what we're commonly used to seeing. All right, so let's do a couple of examples here at the bottom of the page. Find the area and perimeter of each regular polygon described below. Number 1, a regular pentagon whose sides each measure 14 units. So let's sketch ourselves a pentagon here. I'm not great at sketching these shapes. They end up looking a little wonky by the time I'm done. So we're going to pretend that I just sketched a regular pentagon. It's not great by any means. I could keep going and messing with it and making it look better, but not that big of a deal. It's just a sketch. All right, the sides measure 14 units. So the side here is 14 units long. I want to go ahead and draw in my two radii. And we've already determined from up above that the central angle in that position is 72 degrees. Remember, that was 360 divided by 5 is where we get that 72 degree angle. When I draw in the height of that triangle, which I need because I need to find the apothem. That's what that distance is. In order to find the area, we need the apothem's length. So the apothem in this case divides this base segment into two parts, each of which are 7 units long. So in this little right triangle here, I have a side that's 7 units long, and I have an angle that is half of 72, or 36 degrees. Okay, so let's determine which trig function would allow us to use the 36 degree angle, the side that's 7 units long, in order to find the length of the apothem. So from the 36 degree angle, we have the opposite side, and we want the adjacent side, which means a tangent function is our best option. So in this case, the tangent of 36 degrees will equal the opposite over the adjacent. Solve that by a, so a equals 7 divided by the tangent of 36. Now, as we've discovered in class, when we take numbers like this and type them into a calculator, we get a decimal that doesn't look, it's not a whole number, we'll put it that way. Not real pretty. So for that reason, I want to leave this in this form. When it comes to finding the area of the polygon, then I'll substitute that fraction in place of a. The other thing we need to determine is the perimeter of the polygon. So the perimeter is composed of 5 segments, each of which are 14 units long. So 5 times 14 gives us a perimeter of 70 units. And that's one of the answers that are requested. Now let's find the area. The area of a regular polygon is 1/2 times A times P. So 1/2 times that fraction for A, 7 over the tangent of 36, times P, which we've determined to be 70. Here again, with your tangent, when you type that into your calculator, make sure you close the parenthesis after the 36. So the area in this case, 337.21 units squared, since it's an area. And that takes care of finding the area of a regular pentagon given its side length. All right, in number 2, we are looking at a regular octagon whose apothem measures 7 units. Now, as the number of sides increases, I tend to get to a point where I don't really need the whole figure. What I really need is that triangle that's composed of 2 radii and a side of the polygon. Understanding that this side of the polygon is one of 8 sides in this case. Now, for this particular problem, it says that the apothem is 7 units long, which means the distance from, this is the center of the polygon, the apothem, the height of that triangle, is 7 units. Okay, so I know the apothem makes a right angle with the side. I need the length of the side in order to find the area of the polygon and find the perimeter of the polygon. So we do that by using the central angle. Take 360 divided by 8, since it's an octagon, which gives us 45 degrees. Keep in mind that that 45-degree angle is all the way from one radii to the other. I want half of that, so 45 divided by 2, 22.5 degrees. And that 22.5-degree angle is what belongs here. Notice it's in the same position that we had the angle in the first one. Okay, so in this case, I need to find the length of this side. We'll refer to this as x for now. I need to find the length there so that we can determine the length of the entire side. All right, so let's see. Opposite, adjacent, tangent function again. So the tangent of 22.5 degrees equals the opposite x over the adjacent 7. Now in this case, to get x by itself, simply multiplying both sides by 7. So x is equal to 7 times the tangent of 22.5 degrees. There again, that's going to be some decimal that I don't want to have to round it for now, so I'm going to leave it in that exact form. Keep in mind that this length is this segment right here, where we have our x. The whole side of the triangle, which is necessary for finding the perimeter, would be double that length. When you double this length, the only value that gets doubled is the coefficient, not the angle. So here the 7 becomes a 14. The tangent 22.5 degrees is unchanged. We have not changed the measure of that angle at all, so doubling it in no way changes that angle either. And this would be the length of the side of the polygon. Okay, from that length we can determine the perimeter. The perimeter is 8 sides, each 14 times the tangent of 22.5 degrees. So in this case, 8 times 14 tangent 22.5 degrees is 46.39. Now, in this case, I am writing this as a rounded answer for the perimeter because the perimeter was requested. If I were asked for an exact answer, then I would have taken 8 times 14 only and left the 22.5 degrees as part of the product. Now let's find the area. Area is 1/2 times the apothem. Remember, the apothem is what was given, 7, times the perimeter. Now here I want to use the entire perimeter, not that rounded value. So 8 times 14 tangent 22.5. So 1/2 times 7 times 8 times 14 times the tangent of 22.5. The area is 162.37 units squared. And that takes care of our second example. Now the third example, in each of these we're given a different value. In the first one we were given the side length, in the second we're given the apothem, and in this third one we are given the radius. And we're going to see how that affects the solution in general. So we start with an isosceles triangle that represents one of the 10 triangles that would exist in this polygon. So at this point up here, this vertex, that's the center of the polygon, and this bottom segment represents a side of the polygon. In this case, the radius, which is here from the center to the vertex, is 11 units long, which means this one over here would also be 11 units long. When we draw in the height, the apothem, which we need in order to find the area, and we also need the length of the side here in order to find the perimeter, which in turn helps us find the area. So we start the same way. Find the measure of the central angle, 360 divided by the number of sides. Since it's a decagon, we're dividing by 10. That tells us the entire angle from one radius to the other. Divide that 36-degree angle in half by the apothem, and we get an 18-degree angle in this case. Now, in this problem, I need to determine the length of the apothem, which is the adjacent side. And I need to use the 11, which is the hypotenuse of this little right triangle, in order to do that. So if I want the apothem, then I'll use adjacent and hypotenuse, which is cosine. At the same time, I need to know the length of this opposite side in order to find the length of the entire side of the triangle, which is the side of the decagon. That is the opposite side and the hypotenuse. Notice that's two different trig functions. We need the cosine function to help us find the apothem, and we need the sine function to help us find the edge of this short segment here, which in turn will give us the length of the side. So we have the cosine of 18 equals the adjacent apothem over 11. Multiplying both sides by 11, we'd get 11 cosine 18 equals A. And that there again would be a decimal if I were to type it into a calculator, so we're going to leave it in that exact form. Now let's deal with this side x. X is the opposite over the hypotenuse, so the sine of 18 equals the opposite x over 11. Multiply both sides by 11 to get 11 sine 18 equals x. X, you'll recall, is half of the side, so the side of the polygon would be double this measurement, 22 sine 18. And remember, you're doubling the side, you're not doubling the angle. Whoops, that's not equal to x. That's equal to the side length. Okay, so from that we need to find, we have the apothem, we still need the perimeter. So back up here to the top, the perimeter is 10 sides, each of which is 22 sine 18 units long. Exact answer in this case, 220 sine 18 for the perimeter. And this would be in units for P. There again, I could get the decimal version of that if I needed to. In terms of the surface area and volume where we're headed, you're going to want to leave it in this form. Area of this polygon, 1/2 times A, remember A is here, 11 cosine 18, P, 220 sine 18. And all of that should be able to be typed into the calculator. Now remember, most calculators will open a parenthesis prior to that 18. Make sure you close it here and close it on the sine function. So in this case, 1/2 times 11 cosine 18, close the parenthesis, times 220 sine 18, close the parenthesis, 355.61 units squared. And that completes finding the area of a regular polygon given either the side length, the apothem, or the radius.